Oi, mixture of depths. This is a pretty cool Google paper that came out back in, I want to say April or so. Yeah, April. They're taking the mixture of experts idea and the early exiting depths idea, kind of combining them, getting some crazy good performance slash efficiency improvements that seem to have a lot of potential for different ways to toy around with them and make very interesting models into the future. Very excited for this one. Before we get started, like, subscribe, comment, all the YouTube things, hit the bell. If you want to support me financially, you can hit that join button down below or hit my Patreon link as well down below. Options are 1, 3, 5, and $10 per month. Thank you to those who are already doing so. I very much appreciate it. You can schedule a consultation with me. Also, link in my link tree to like a Zoom type hour-long meeting paid if you want to pick my brain about something. And other than that, oh, disclaimer, of course, disclaimer. Pause the read if you'd like to. But yeah, let's get to it. We are getting right into their main results here. On the one hand, you can train in a mixture of depths transformer that improves on the vanilla ones by as much as 1.5% on the final log chance training objective for equivalent training flops, aka ISO flop, right? And while taking an equivalent amount of wall clock time to train. So they're saying just full on match it in terms of compute, and we can get better performance if we use mixture of depths. But on the other hand, if you wanted to instead, you can train a MOD transformer that achieves the exact same loss, but with far less actual consumption of resources, upwards of 50% it seems per forward pass. And I believe they're referring to inference isoflop comparison. So if you want just very efficient models, this is also a good way to do that. It's both, you choose. Do you want higher performance or more efficiency, or like probably some combination of both? The results seem pretty good, it sounds like. Let's get into the actual method though. So, core idea being we have a router, right? And that router determines if we should even use this layer at all, right? There is an option to just do a complete skip past the layer entirely. However, when I say skip, it's kind of weird, right? Whereas in a regular MOE, when you have a router, it just determines which expert you go to. Here in MOD, it determines if you actually use that layer at all. And think about this, you're doing this per token, right? So meaning that your actual mixture of depth transformer has a smaller total flop footprint, right? Because some tokens just don't go through the entire block, which I believe also means in the self-attention mechanism, you end up with a smaller total attention quadratic matrix, right? Now, when you compare it to early exit based strategies, right? In early exit, you dynamically decide if you should just end right here and use your final output embedding. Here, the stark purple is a vanilla transformer, just uses every single layer for every single token in the sequence. Early exit, some tokens use every single layer, many tokens leave before then and just output. Whereas what happens in mixture of depths is that a given token in the sequence could just use any layer. They're still in order, but it will just randomly skip a couple, then use, then skip, then use, right? The given layers. Now, given that it's skipping entire layers for different tokens, you do end up with fewer flops per forward pass than a regular transformer, which, as I said, is not only in terms of number of layers going through. Like, let's say we choose half of the actual, you choose the rate of skipping you want to do in how you encourage the router to act, right? So not only are you skipping raw flops just going forward, but in terms of RAM, the query times key mapmul during self-attention, if you were to do half the layers being skipped, you would end up with a 25% less flop intensive actual query times key matrix, the sequence by sequence uh, at the end tensor, right? So in terms of RAM consumption, you can, in that example of just half the tokens being used, being skipped, you end up with a 25% decrease in the RAM consumption of your attention mechanism, which is huge. And I believe later in the paper, they actually do a much smaller capacity, as in far more skipping than just half. But keep in mind, it also means whenever a token is chosen to skip the current layer, that means that token literally is not in the attention mechanism. Like it cannot be a query itself or be a key value for a given query, right? So that begs the question, like, would that hurt actual performance or not? Well, the hope is that the router is intelligent enough to actually tell whether it should even be in the attention mechanism, right? The hope is the router is smart enough to know, oh, it's not even going to need this token in this attention mechanism right now. No biggie. Whereas if the router cannot learn that, you would expect a huge performance decrease. As a control, a baseline, they just use randomness to route tokens, aka like layer or block dropout effectively. And they wanted to clarify that doing random routing of skipping layers would not work very well. So this thing they developed is not quite trivial. If you were to do randomly blocking out layers throughout training, you would end up underperforming a regular vanilla transformer model. Now, there's two different ways you can actually deal with routing. The one they're doing here today, I believe, is expert choice routing, which flips the traditional recipe of routing on its head rather than having, like, kind of reverses it. Rather than having tokens choose the path they prefer, each path instead chooses the top K tokens based on the token's preferences. This ensures a perfect load balance during training since K tokens are guaranteed to be shuttled to each path. Every single path chooses its top K tokens, right? As opposed to each token choosing whatever path it wants to go to. And when each token can choose the path it wants to go to, that's when you learn the problem of like all tokens choosing one or two, like a few paths. Whereas here, they all get every single path guaranteed gets K tokens for our top K mechanism. So you end up with very even distribution and therefore don't need a load balancing loss during training. However, the problem is, first, it could result in over or under processing of some tokens, since some tokens may be among the top K for multiple paths or for none of them at all. So when the paths themselves choose what tokens they want based off top K, what you end up with is some tokens that could have maybe benefited from running through some path won't actually make it into the top K, or vice versa, or in contrast to the opposite like version of that problem is that when you're choosing top K every time, it might be the case that like this expert should have only actually like looked at K minus N tokens, but because you're doing top K, you're forcing the expert to actually look at and calculate K tokens, as in doing too many tokens, right? So not a perfect method here per se, but it is a kind of flipped version of what you're usually used to with like a routing mechanism and load balancing loss. The other issue being that it does require that the expert choose the token, meaning things kind of happen in reverse a little bit in terms of the causality of the model. And now suddenly you have the issue of, okay, during inference time, how am I going to specify which token goes to which expert if during training time I was doing it in a like a reverse causal way, but I now during inference by definition can't do that, have to do it in a causal way, right? So we're just talking about a visualization of that stuff. Token choice routing, right? Is where every single token gets to go where it wants to, and some experts end up with not enough tokens, right? So this one just has a gray. Some experts get too many. This expert right here gets red, orange, and the purplish pink one also wants to go but can't. It can't fit, right? For our top K, whatever. Expert choice routing, the experts themselves choose the tokens that they want. They all just grab their top two, right? But you end up with they might not grab some tokens at all. And then when you use expert choice for mixture of depths, right? Remember we're doing sparsity and we're actually having lots of tokens skip things. It's just the layer itself is the expert, the entire block attention MLP layer, and it just grabs whatever top two or top K whatever tokens that it wants to calculate, leaving most of them sparse, which is kind of the purpose of mixture of depths. Okay, now on to the problem I mentioned. Top K operation is non-causal. This means that whether a given token's routing weight is among the top K for the sequence depends on the values of the routing weights for tokens that come after it, which we don't have access to when autoregressively sampling. So what we're saying here is the what happens to a given token depends on the tokens that come after it, because the tokens that come after it have that go through that router, right? And the problem is during inference, we literally do not yet have the tokens that come after it. So there's no way to use that whole top K mechanism because it's non-causal, right? What we do instead, well, actually, they tested two methods to work around this problem. The first being just a simple auxiliary loss, which I believe is the other option of letting tokens themselves choose where they want to go, which is not ideal. And then the second method, because auxiliary losses, or load balancing losses anyways, are just notoriously difficult to tune. And the second method introduces a small auxiliary MLP predictor akin to like a second router almost. So there was the first router was used during training, right, for the whole top K thing. This is a second router that uses an MLP just for sake of more expressivity, and that receives the same inputs as the router, except with a stop gradient, but with those but whose output is a prediction whether that token will be among the top K or not in the sequence. So this second router, what it is trained on is the results of the actual first router. The second router is used only during inference. The first router is used only during training. It is the job of the second router, the inference router, to emulate, to simulate what the results would have been of the training router, right? Despite the fact that the training router was non-causal, got to look at tokens from far ahead in the future, whereas the inference router is causal, only looks at the tokens you currently have already that you can look at. And this method does not affect the language modeling objective and empirically does not significantly impact step speed because it's just one single MLP, a relatively small one, I would imagine, not quite sure. And so all you have to do is an extra MLP in there. That is, whereas usually during inference and during training, your router is a linear layer. Now it's an MLP, not a huge impact on speed, and we're gaining so much speed elsewhere from skipping layers that it's totally okay, right? But in effect, this inference router is simulating what the training router was doing, but just during inference, right? And it was trained off of the actual data from the training router. Every time during training, the training router gave out its top K choices. Those choices were used to train what will later be used during inference, the second router. Here we have some comparisons of baseline is this darkest blue, it looks like almost black, and then the lightest blue is mixture of depths with a 12.5% capacity, meaning only 12% of the layers of the tokens actually go into a given layer, and it's every two, I believe, meaning every other layer is a mixture of depths layer, while every other one is a regular dense layer, I believe. And then there's also the regular, I guess, navy blue or so is a 50% capacity sparseness. And then the orange, another baseline, is a 50% capacity sparseness, but it uses random routing as opposed to our two learned routers, right? And that's also, they're all every two. I believe they found that just doing every other layer as a mixture of depths layer, it just performs way better than doing every single layer possible mixture of depths. It adds some consistency to the model. Like you can think of it conceptually as like it is giving some predictability to the model as to what it should expect whenever, rather than like a single token could skip every single layer, whatever it is, right? You don't want to do that. In terms of flops per step, we compare our baselines to our mixture of depths. Significantly fewer flops per actual step. I believe autoregressive steps what it's saying. And then steps per second, you can do a good bit faster inference, right? So doing an actual isoflop comparison, meaning holding the actual inference flops equal, you can choose, do you want a same inference cost model but better performance than the baseline dense transformer, or do you want a same performance as the baseline dense but significantly faster inference? Or you can also choose a Pareto optimal combination between those two. And there was no fall off curve for this, meaning that the optimal MOD transformer is that which, like assuming an isoflop consistency, is that which uses as many flops per forward pass as the isoflop baseline. This finding allows one to directly predict which sized MOD transformer will perform optimally for a given isoflop training budget. Also, separately, empirically, they found that it's better to add depth than to add width when adding flops to the model in this MOD setup. And testing different capacities, as in different removal rates for how often to skip tokens, they found it's best to use an MOD model where 12.5% of tokens get used in a given layer. and doing this not just for every layer, but for every other block. So like this right here, we have regular dense 100% capacity layers interleaved with mixture of depths layers. And very interestingly, when you look at towards this left piece, right, it seems, oh, okay, just randomly or whatever, like intelligently, but it seems somewhat random, right? Layers are kind of getting used. But you notice some density right here at this sequence in the step, at this actual token in the sequence, right? Sometimes some tokens get just really densely used. Very, very interesting thing going on right here is the network does seem to be consistently like there are patterns in the sense that, oh, some tokens are just difficult, and the network does give like almost all or all of the layers towards that token in the sequence. Very cool. If this were not the case, I would almost imagine the model to like perform close to the random stochastic baseline. But given the fact that it is saying, oh, sometimes some tokens are crazy difficult, I'm going to use all or almost all of my available layers, that is a good sign to me for sure. Preliminary analyses suggest that the tokens that engage with blocks more frequently, aka that the dense one column right here, are correlated with output predictions that have higher entropy, which possibly corresponds to predictions that are more difficult to make. So there is a correlation between whenever the model gets dense right there for that token and the actual model's logit outputs, they tend to have higher entropy, aka more uncertainty. So therefore it is during those high entropy times trying to use more of its compute on that difficult token. They said here, I didn't delve too deep into it, but apparently the performance improvements offered by MOD compound with those of MOE. So I believe they did end up trying to test that out at some point, and they called it MODE, mode, mixture of depths and experts, I presume. So intuitively, a token might learn to route around blocks because the prediction being made at that step is easier and hence does not require as much compute. However, this strategy is undoubtedly not all that the network learns. If a token does not participate in self-attention at a certain block, then later tokens will also not be able to attend to it. Thus, whether tokens decide to route or not impacts both the current step's prediction and future predictions via causal self-attention, and how the network balances these effects is guided by their influence on the overall language modeling objective. So what it's saying there is that whenever a token skips a given layer, right, that token is now not available in the attention mechanism. It cannot be both, it does not act as a query, and it cannot be referenced in terms of being a key or a value. Therefore, the model probably is not just learning how difficult a given token is, it's probably also learning, the router, sorry, is learning what tokens are useful as keys and values for the attention mechanism. Likely, anyways. And this insight opens the door to potential MOD variants that decouple the routing for queries, keys, and values. I cannot wait to see paper on that. That'd be so cool. This is a huge way to save RAM without having to go to a full-on linear model or anything, still using transformers. You could even imagine a kind of long-term memory. Perhaps there are tokens that would be extremely valuable as keys, regardless of whether it is useful for them to also be among the queries at the step of their occurrence. This, I think, is a super cool way. Just route whether or not a given token should be included in the attention mechanism as a key value. Love, 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 love this idea. Cannot wait to see a Google paper discussing this and actually like delving deeper into it. Could drastically allow for huge increases in context length if it works. And one can imagine extend this idea further by routing between even more types of computation. For example, perhaps some tokens are routed to memory lookup functions and others are routed to tool use functions. I do like the idea, they're just speculating now as to like how might we really expand out how we're routing this. I would love to see networks being made soon that are just fundamentally wildly routed as like, do we route you to a Mamba right now, or to an attention mechanism right now, or to a convolution right now, or to a feed forward network right now? I would love to see some really intense, crazy routing models that I believe would probably, they can't use traditional load balancing loss. I would bet that'd be way too hard. I assume. I would bet instead they would probably have to use the method today, the expert forcing, I think it's called, expert chosen routing, where you actually have the whole top K first router during training and then the learned router to use during inference. I'd love to see some real crazy going past the very boring at this point MOE setups that we currently have today. And notably, If one wants to introduce an expensive computation, such as the attention mechanism, for example, then this can be offset by setting its capacity to some small amount, and hence by routing only a small number of tokens to it. So this essentially, this idea of routing might allow for even more expensive computation types than attention, maybe like a cubic type setup or something like that. I don't know. That could be super interesting to see how those work in the future, given that we don't actually have to do the entire cubic, for example, computation costs per sequence. We might be able to just through routing make it relatively small, but still gain the benefits of said crazy demanding computations. Very, very cool. What are we doing for my understanding level today? I'm gonna say I want to say 4 stars probably. I'm pretty confident I get what's happening here. There was a time or two where maybe I should say 3 star or two or something, where it's like, did I understand something perfectly? I could be, it's one of those things where it's like you could be overestimating the degree to which it'd be easy to replicate if you were to do so. Because maybe there's like thing I'm missing that I'm not thinking about very well. But I'm pretty sure this was all pretty self-explanatory. Seemed cool to me. I enjoyed it for sure. I'm gonna go 4 stars today. That's my bet. Maybe 3.5 or something. But anyways, if you enjoyed this video, like, subscribe, comment, all the YouTube things. Join the Discord to discuss the Mortuna Dorks. Follow me on Twitter and connect on LinkedIn. If you would like, you can support me financially through $1 a month, 3, 5, 10 bucks a month options. Hit that YouTube join button down below, or link to my Patreon also in the description to support me. Thank you so much to those who already are. Really appreciate it. If you want to schedule a consultation with me, an hour-long paid consultation, the link to that is also in my link tree, just like a Zoom meeting type hour-long thing to pick my brain. Go ahead and do so. And yeah, I'm gonna say end of video.